All right. So we talked about selective laser sintering last class. And today let's talk about another process, which is the material jetting. So the material jetting process is in 3D printing is similar to its 2D counterpart, right? So the printer selective print a layer of liquid photopolymer. The difference between this inkjet-based process and the vat photopolymerization is there's no vat, right? So the material will be injected onto the printing platform, and then a UV flash lamp is utilized to cure the printed area. So if you look at this illustration figure, here shows how it looked like. So this is the jetting head. It can move in the X, Y direction, as well as there's a motion in Z direction realized by this printing platform, right? This printing platform can move upward and downward to have a Z-axis motion. And here you can see the printing material is jetted on the printing platform, and this UV light will cure these material layer by layer. So there are different colors and support material, as well as the printing material utilized in this process. And it is suitable for printing the part with extremely fine details. That is because this kind of jetting system can achieve really high resolution. And there are several existing machines which achieves the very fine details, good features. Another good part is the multi-material and multi-color capability, because it has, as you can see here, there are quite a bit printing head. So that makes this multi-material printing possible and multi-color printing possible during the printing process. And we can look at this illustration. See, here shows how it would look like, this process look like. And the UV lamp is curing the material. And also at the same time, the material is jetted onto the printing platform, and then this UV lamp cure them. That's how it looked like. That's the Stratasys J750 machine, which is located in the Amprint Center. Another machine is the 3D system ones, right? Basically they have the ProJet MJP series, and they are the multi-jet printing process. And they have similar process as the Stratasys has, but the color selection is less than the Stratasys machine. So again, this process can be dissected to different sub-steps. First, slicing of the 3D model, and then jet the material there. And of course, you want to move the printing platform to have I mean, after jetting the material onto the existing layer or the printing platform, you want to make sure the height, the layer height is consistent. And then the UV light will be applied to cure the photopolymer material. And then this will be repeated until the whole process is completed. So the centric process for this material jetting is the jetting process, right? How you put one droplet of the photopolymer material onto the existing layer or the printing platform. And so the nozzle diameter of the printer is pretty small, as you can see here. It's only like 40 microns something. And there are quite a bit nozzles per channel, right? One channel have one type of material. So there will be 92 nozzles for each of the channel. And there are 2 channels for one printing head. So as you can see here, this is a zoom in view for the droplet drops onto the printing platform or the existing layer. So if we look at an illustration of the printing head, as you can see here, there are those nozzles on the same printing head. There are different modes for the printing. There's a high-speed mode. Basically, it prints the block, travels down and back each lane of the slice. Also, there are high-quality mode. So the quality of the speed for printing, they're usually contradict to each other. Means if you want to have a high speed, the quality of the printing need to be lower, and vice versa. That means a high quality mode usually leads to a low speed. So as you can see here, the gap between each of the dots is usually 80 to 100 micron. So if there's a question asking you if the printing head is 65 millimeter wide and there are 192 nozzles, so what is the z-axis drop spacing on the head? So basically, if this is the y-axis, it's asking you to compute this, right? And similarly, if you can also compute the if you can also compute, you can also compute the spacing in the x-axis direction compare with the spacing, droplet spacing in the z-axis direction, right? Similarly. So how you compute for the first question, which is the y-axis drop spacing on the printing head. So what you could do is basically you have 192 nozzles, so the spacing will be 191 instead of 192. For example, if you have 3 nozzles, let's see, 1, 2, 3, right? Then you have 2 spacing instead of 3, right? Similarly, you have 192 nozzles and the spacing will be 191. And how many and what's the total total width of these amount of spacing? That's 65. So then you can compute what is the value for a single spacing, which is 65 over 191. And turns out you will have 340 micron for the y-axis spacing. All right. And you will know basically the droplet spacing in the y-axis, that is in this direction, is not the same the one in the y-axis, because it's totally independent to each other. So the dimension of the printing head in the x-axis is different from the one in the y-axis. So you cannot simply use this value to represent the droplet spacing in the x direction, as well as there's another factor for this is in the x-axis. The spacing of the droplet is controlled by the motion of this printing head as well. So basically, you can imagine with certain time constant, with certain time period, there will be a series droplet created along this line, and then this printing head move a distance, and another line of droplet will be printed. So basically, you are measuring the distance between the two lines, right? So that is controlled by the motion and the jetting frequency of this printing head, right? So you should understand that is totally different from what we compute here. All right. Let me erase this. It's a little messy. All right. Okay. Let's move on. So there's another step is the leveling. So that is similar to what we had in the selective laser sintering, which is to make sure the material is leveled well, and there's a leveling ruler which is used to level the parts, right? And once the material is jetted, the light source, UV light source, is applied to cure those photopolymer material. And here you can see the UV lights are located here. I mean, different printing head has different setup. The one we see in the video is different, right? Basically, it is on the back of the printing head. But here, this one has two on each side of the printing head. And for this process, usually the layer thickness can be achieved in between of 16 micron to 30 micron. And you can make change because there are different modes, right? You can select the high speed mode or high quality mode, and that will change the layer thickness during the printing. And again, a smaller layer thickness requires much longer time, and that's how it works. So the support material is necessary for this process. It's similar to the fused deposition modeling, right? And similarly, the features with a negative slope or overhangings will require the support material. And so for this kind of support material, it's desirable to be easily washed away or dissolved in some solutions, right? That again requires some post-processing to remove the support material. I think that's quite similar to what we had previously. And as I mentioned, the jetting-based process has a higher, quite good resolution. And the relationship between the resolution of their prints and the accuracy of the parts are something like this. So for example, you have a high resolution, which means a 600 by 600 times 1600. What does it mean? That means, well, you will have 600 drop per inch in both and y. This represents x and y, right? And this represents z. So the accuracy, what accuracy represents in this case is, well, that how different the printed parts versus what you designed, and that will be used to estimate whether the printed part satisfies the design tolerance, whether this could be assembled with the other parts for a assemblies or some movable parts. And again, the higher resolution means there are more dots, more droplets in the same area of the prints. And in other words, the distance between each of the droplets will be smaller. And that means the smallest feature this printer can achieve is related to this distance. So higher resolution usually lead to a higher accuracy, right? Again, that's similar to what we had in the VAT photopolymerization process, the stereolithography, right? And if we look at some some parameters for the printer, PolyJet printer, for a high-speed prints, the layer thickness is the 28 microns, and there are 3 material can be used, and 3 printing head. Another 2 support printing head for the support material. If you choose the high quality one, then you will see, well, the layer thickness becomes half of the one in the high speed mode, and more material can be used in this case, and more printing head involved. But if you want to have a high mix, so literally it's a mix of those parameters, right? The layer thickness is still 28, which is similar to the high speed mode, but the material can be used is same as the ones in the high quality modes. Again, the model has the printing has, right, 6, same as this one. It's kind of combination of the first 2 modes. Lower printing time, lower accuracy, but more material can be used. So for the same parts printed using 2 mode, high speed and high quality, if you have a zoom in view of these regions, as you can see here, since there are a larger layer thickness in this high speed mode, so the step effector here, see, is worse compared to the prints in the high quality modes, right? But the trade-off is time versus the printing quality. You want to make your decision based on a specific case, whether you want to have a higher accuracy or you really want to have a higher efficiency. to have a less time for the prints. That's what you need to decide. All right. So an important step for this kind of printing is to load the material. And as you can see here, there's a cabinet, right? You can see here. Basically, you have the material cartridge installed in the printing cabinet. I mean, in the material cabinet. And what you want to do is you need to take off the old cartridge and replace it with the new one with full with the material in it. I mean, that's there's not much to say, but that's how it look like. And as I mentioned, the material utilized in the PolyJet, basically, it is a liquid acrylic-based photopolymers like the one showing here. And there are different colors can be utilized in the prints, as well as the some of the material property. You could have really flexible material and more rigid ones, and some combination in between, right? So you can see there are really good parts. I mean, for the one showing here, the parts with multicolor or some of the semi transparency can be achieved due to the material utilized in the printing process. And so there are really nice ones, like the one shown here. This is a heart example printed using the PolyJet printer. And there's a concept called digital material. So digital material is the concept for the multi-material. There are 2 or 3 base material, and then you could customize and specify different material in different regions. For example, in this one, there's some relatively rigid region for the vein, right? And there are soft ones for the muscle on this in this region. This could be designed to use the associated material and some third-party material. I mean, some associated software or some third-party software, which is dedicated to design the material for the prints. It's a popular research area for the digital material design for these PolyJet printing. And as you can see here, you could select quite a bit different materials by combining the different inks with different material together. And it turns out you could find, I would say, quite wide range of selection for the material if you select different portions of the 3 basic colors in the ink, right? Here shows you a color palette, which gives you the information of all the available material, available colors printed in the printer. Right. Again, this is another color printing. The skin color is one, and as you can see, the core color is another different one. So you can see how accurate, how I would say what kind of texture and color could be achieved in using such a prints, right? Which is really good. And another good application for this is this kind of clear material utilized. And there are some applications for printing of lenses, right, using this kind of clear material. And let's look at the support material removal. Basically, we have such kind of device for the material removal. And this gel-like support material need to be removed using a water jet. And basically, this material will be washed here. And also, you could kind of pressurize the water a little bit if the material is sticky to, I mean, the support material is sticky to the prints. So you probably want to have a water with little higher pressure to remove them, to remove the supports. Well, there could be also other some selections instead of just using water, right? And also other tools, right? For example, these hydroxide solutions, right? That could be another way to remove it. But usually the water-based one is good enough. I mean, just a pure water with pressure is good enough. Again, the paintings, right? You could easily apply some painting, some colors, actual colors or texture using this kind of painting process. Basically, the material utilized is acrylic based material. So the paints for acrylic material will be good enough, will be applicable for painting the parts printed using the PolyJet machine. So here shows a print, something like this, and then after the paints applied, that's what it finally looked like, which is really good, right? Sorry. There's another process called the hydrographics. So it's a water transform painting. I might just show you a video about it. I think it's worthy to have a video. That's another very interesting process. But in this example, it's like a. Let me just search it on YouTube, and then you should be able to see how it looks like. Just 1 second. All right, let me show you what it is.
That's a Chromebook with the Everything button, so you can find things instantly, from files to apps.
Just wait a little bit.
Online. Who says you can't have everything with the Everything button? Switch to finding things instantly. Switch to Chromebook.
right? That's pretty much what it looked like. So through such a process, you could have a really nice texture on the prints, right? Like the one showing here. After parts taken out of the printer, you can use those hydrographics process to stick this kind of texture on it. Of course, for larger parts or assemblies, you could glue them together for different applications, like the one showing here. It's a really large parts which cannot be printed in a single printer. What you could do is to separate the original object into different parts and print it, and then assemble them together. And that's how you think of some printing some larger parts using a relatively smaller printer. So there are some design for assemblies like the one shown here, this kind of boundaries, which can be used to merge two parts together, right? This kind of self-locking shape, geometry. But the key here is the tolerance. Means you want to carefully set up the tolerance for the two portion. On one hand, you should be able to press fit the two together. On the other hand, you want to maintain a relatively tight connection between the two. So it cannot be too large space in between the two parts. And that's what is the critical process to set up, to find out an appropriate tolerance between the two assemblies. Another possibility is, well, use glue if you do not to disassemble them. If it is one shot, I mean, you just want to assemble them once instead of disassemble them, then you could glue the two parts together. That will be a better, I mean, that will be a easier process, right? So there's another post-processing, which is the photo bleaching. And basically it is a acceleration of the post-processing. As you can see here, you can either use the table lamps or some illumination chamber for this process. You can simply utilize the normal table lamp, which is quite economics, right? And or you could use this nice but expensive device to do the photo bleaching. And what this photo bleaching achieves is to further process the prints to prevent a degradation over times. So if without this photo bleaching, the parts could have a slightly, I mean, it could become slightly yellow with time escapes. So that's how the photo bleaching helps, right? Here shows you an example. If there's no photo bleaching, that's how it look like after time, right? After some time. So if the photo bleaching is conducted using the chamber, that's how it look like, right? Or you can simply use a table lamps, which is also good compared to the one before the treatment, but a little worse compared to the one processed in the chamber, right? That's how it look like. So these are the steps for the photo bleaching using a table lamps, which could be, I mean, which is quite available for us, right? The lamp is much more cheaper. I mean, is much cheaper and accessible compared to the chamber. And you can go through the details for what to do in using the lamps for the photo bleaching. And sorry. So if you ever look at the same parts prints in the same process, there are some difference. It is supposed to be clear parts, right? But there's some yellow at this corner, but more clear at this corner. The reason for this situation is, well, because the light has the UV lamp on the printing head has a position, and on the same platform in different regions, the amount of light are not balanced. That means as in some region, there are more UV exposure, and in some other region, it has less UV exposure. So in that, because of this, the final color of the prints will be different. So this is not, I would say, it cannot be resolved. So we can only try to avoid this as much as possible. So in that sense, you don't want to build some small parts next to the tall parts. In the case, the UV exposure will be dramatically different, and that will make the difference between among parts even more significant. All right. And as you can see here, shows a very tall parts, and the one near it will have a quite significant difference between the one which is far from it, right? That is because the different UV exposure, and this high part could hide the light. That's a very interesting situation in this one. All right, let me erase this. And a polishing sometimes is necessary, especially for some smooth and clear surface. You want to sand it or using other way to polish it. For example, for the printed lenses, right? Definitely you want to have a clear and smooth surface. And here show you some of the steps for the polishing. And I don't want to go to details, but you can look into how it can be achieved, right? So for some of the parts like this, if a polish is conducted, you can see the total is totally different, right? Before and after the polishing. And some of the dyeing of the translucent models, right? Like this clear part of the process becomes a red part, and also this Disney castles can be colored like this using this dyeing process. So there could be other process to coat a lacquer layer onto the printing surface, and what as you might see in some previous figures, the parts with a shine and metal-like surface that could be achieved using this kind of process. Sorry. Sometimes the thermal treatment is necessary to improve the material properties to release the residual stress for the parts. And again, it is a heating in the oven, programmable oven. And after sometimes the heat up, these kind of parts can have improved material. Sorry. So the metal coating is similar to the lacquering. So what you have is this kind of coated part using this process, right? And it's for the one with this coating, it has a very good surface and it achieves at same level as the one manufactured using other process. And so the last post-processing is this kind of a physical post-processing. You can drill holes or use the tapping tools to create the thread or enlarge the drilled holes. So just like what you did to other polymer-based parts, right? All right. Let's have a break and let's come back at 10 a.m. All right. Let's continue. So let's talk about some of the computational elements of the injection print, and also some properties, printability problems of the inks used in the inkjet printing. So there are two major type of printing head. One is a thermal inkjet, and also a piezo inkjet. And as I mentioned in the last class, the diameter of the nozzle is in tens of microns, right? And there will be hundreds of nozzles arranged in one or several rows. The voltage signal will be utilized to control the injection of the droplet. There will be some waveforms utilized to control the injection of the droplet. Another thing is the motion, right? The head could move at a speed of a meter per second relative to one another, and the droplet velocity are on the order of 5 to 10 meter per second. By composing the two motion, you could have a series of droplets, a line of droplets, another line, and again and again. This kind of pattern could be achieved by composing the two motions. Sorry. Also, the printing head is typically on order of 1 millimeter above the printing platform or the substrate. So let's look at the two injection types. One is the thermal one, thermal prints. As you can see here, this is the thermal-based printing head. And a 10 to 2 micron, 10 to 20 micron square a resistor heater is located above the orifice, right? As you can see, actually this one is a flipped view. The droplet will come out here. So it's upside down look of a printing head, a thermal printing head. So the ink first, let me have a pen to have some annotation. So the ink come in the this region, and then the heater will heat up the ink and generate a bubble here. And this bubble will push out a droplet. And then the droplet will have a speed to drop on the substrate. That's how this kind of thermal-based inkjet printing head work, right? Also, the piezoelectrical transducers could be utilized in this case. Again, this is an upside down view, right? The ink come to here, and there's a piezoelectric transducer installed here. So what it does is, with certain voltage applied, this part could have a deformation. It will be deflected, and this deflection will push the droplet out of this region, and that's how the piezo-based process work in this printing head. So let's look at the droplet. So what kind of droplet you want to form for the printing process? And if you have a lower surface tension, so the droplet will be elongated. And in contrast, how about a higher surface tension? Then the droplet will be looking like a sphere shape. So if the two droplets, a elongated one and a spherical one, the two drop onto the moving platform during the process. So what will be the droplet look like when it's on the printing platform? If you have an elongated one, like something like this, right? These are elongated one. And basically, the droplet will streak on the platform. And that will make the accuracy of the prints unpredictable. So the inkjet printing head is very important for a inkjet printing, and some of the printing head can cost from 750 to over 5,000, right? So that makes this part very expensive, and usually when there's a long time you don't use it, you don't use the printing head, you want to have a cap on the printing head. The reason is you don't want to have the ink solidified and the whole printing head gets stuck by the solidified ink, and there's no way to fix it. You have to replace a new one, which will cost this much, right? Which is quite expensive. So remember, if you have a long time not in use of the printer, you want to cap it. I mean, put on a cap to the printing head such that you will save a lot of money. So the printing head is vacuum, and that is for preventing the liquid from oozing. Sorry. And again, the capping is very important because the ink could dry out and just make the whole printing head not working. And that is what we want to prevent if there's a long time we don't use a printer. You want to cap it, right? As I mentioned, the voltage controls the droplet during the printing. If the droplet drops too fast, there will be splashing. So you don't want to have a splashing during the printing process because that will make the printed pattern unpredictable. So an appropriate voltage is necessary to control the droplet velocity. And another thing is the droplet volumes. That is the amount of printing material in each of the droplets. So if you have a good control on the volume, that will make the part more precisely predicted. So if we look at this resolution with the drop spacing, again, this kind of a resolution give you the information, how many dots will be an inch of the an inch long region, right? So if you have a resolution, you should be able to easily convert it to a spacing between each of the spot. How? By the definition of dots per inch, right? So for an inch, there are 50 dots. Then what's the dots? What's the spacing between those dots, right? That's how you compute. Same thing happens to all these numbers. You can easily convert it to spacing, and vice versa. With the spacing, you should be able to convert it to the dots per inch, but you want to round it, right? So this spacing after the computation, it could be some decimal numbers for the DPI, and there's no way to have a decimal number for the DPIs because it means dots per inch, right? So you have to round it down probably, because yeah, that's a safer way to have a resolution, rounding down what you have if you have the spacing, right? So if we assume the droplet is a perfect sphere, and you could have this equation to compute the volume of a droplet, right? So also, if you already know the volume, and again, if you assume this droplet is like a sphere, you could compute the diameter of the droplet. So for example, in this question, you already know the droplet volume is this one, 30 picoliters, right? And what is the diameter? So you can substitute the number here and use the equation. You have a radius and 2 times radius, that is the diameter, and something like this. So a critical part for this computation is unit, right? Since the droplet is very small, usually its volume is small. So it's not liter, even not milliliter, it's picoliter or even smaller unit. So a conversion of the unit, that's a critical part you want to keep in mind. So another calculation is the nozzle pitch. As you can see here, for a printing head, you have such amount of nozzles. And what is the spacing between the nozzles on the printing head, right? Another one is this drop spacing. For example, if you have a printing head and this printing head is moving along this direction at certain velocity, and also this drop head exits the nozzle at a certain velocity, how this droplet look like when they arrive at the printing platform. So here shows you a possible pattern. And as you can see here, there are some spacing between each of the lines. And what you could do is shift this printing head a little bit and print another set of line, and such that you will have a more solid layers. That's how a multi-pass prints look like. Of course, you could have even more passes to have more material printed on one layer, and that's the but that's the basic multi-pass printing illustrated in this figure. So as I mentioned, the droplet, how the droplet look like on the printing platform is affected by the frequency of the droplet exit the nozzle, as well as the printing head moving velocity. And you could think of what would be the relationship between these two factors and also the and also how it looked like on this how it looked like the patterns of the droplet on the printing platform. So here you could try yourself to derive a relationship. I could show you. We can have a little discussion next class, and I will show you how it looked like. So another chunk of calculation happens for the printability of the ink. So how you understand printability? Basically, that measures how easy or what is the property of the ink during the printing process, and how this will affect your decision, the parameters, and also the fundamental printing principles. So there are several important factors: the viscosities, surface tension, and the inertia. These are the critical ones you want to take into the consideration for a printability of an ink, right? So there are different characteristic numbers representing the printability: a Reno number, a Weber number, as well as a Onsor number, right? So so for the Reno number, what you have is a sum of the ratio of inertial force and also the viscous force. So you have all these parameters known and substitute to this equation. Then you will have a ratio between the inertia and also the viscosity force in a moving fluid. So just to keep in mind what you need by looking at these parameters. Also units, right? The units is very important. Make sure you have the right units before plugging in them into this equation. So the Weber number gives you the ratio between the inertia and the surface tension. A high Weber number usually lead to a droplet splashing and a breakup on the substrate. And on the other hand, a lower Weber number lead to a droplet that land on the substrate and contract. So it's similar to the Reno number, but on the denominator, it's not something about the viscosity. Instead, it's the parameter for the surface tension, right? And again, plug in all these numbers, and then you have the Weber numbers. So this on-source number actually it combines the Reno numbers and also the Weber numbers. And what it has is something like this, right? So so how you use these numbers for the printability of a fluid of an ink? So that is very interesting. You could look at this chart, right? So on the horizontal axis, it's the Reno numbers, and the vertical axis is the on-source numbers. So if you have some ink forced into this region, that means it's too viscous. And if you have some ink falls into this region, well, splashing happens quite a bit. Anything in this region, the energy is not sufficient to form a droplet. And anything here, there will be a satellite droplet. That means there will be some smaller droplet forms with a larger one, so which is also undesirable. So a safe region is here, right? You want to look at this, whether the ink falls into this region or not. If that's the case, that means this material, this ink is quite printable. And that's how you could utilize this these numbers, the OnSearch as well as the Reno number. So there are some calculator which could be utilized to compute this as long as you plug in all these parameters. It gives you all these numbers, right? And it shows you where the ink located in this graph, and tells you whether the ink is in the printable region or not. So another calculation is the conditions for the stable lines, right? So what is a stable line? So if you look at this one, so here you have all these dots separate, and then it becomes more like a linear line, and this one is really good, but this one, you have a large region. That means, well, there are too many dots in this region, and in some region is still good. That means they have appropriate material, and some other regions, it looks a larger region again. So how could you achieve a stable printing? And you could utilize this equation. So in this equation, the W is the width of the bit, right? And to find out this width, what you want to do is to plug in those parameters: droplet diameter, droplet spacing, also some of the angles, the equilibrium, contact angle in degrees, right? Please remember, it's not a readings, it's degrees, right? And put them together, you will have a width. That's pretty much all for the inkjet-based printer. And there will be a homework associated. I will release it today. And again, the due time will be tomorrow. I'm sorry, I mean next Tuesday, 10 p.m. So I think I must stop here. I don't want to go to another lecture without a complete introduction of it. So yeah, if you have any question, you can stay here and ask. Otherwise, let's meet next Monday. All right. Oh, by the way, the kit for the RC cards, it should be here tomorrow, and by Wednesday I will let the RTA to pass all the parts to you guys. Sorry for the late. I mean, there's some delay for the ordering during the breaks, but hopefully, I mean, luckily we had it done last week, and it will be here by tomorrow. All right. Oh, another thing is the groups information. I believe all of you have a group right now, and again, contact with your group members, and I would recommend you to set up a regular group meeting and divide the tasks. So there's a portion of grades part of the grade falls into the teamwork. So I had cases. There was an individual in one group who was complained by other by his group member, group mates, that he didn't do anything to the project. So I got confirmed with everyone, and I have to take off some of the grades for that individual's final grade. So that is important. Basically, you want to communicate well, divide the task reasonably, and more importantly, execute it timely, right? And do a good communication, right? I know that could be challenging, especially approaching the final weeks, right? The due of the final exams and final project. It could be overwhelming, but still you want to maintain a good communication with each other and let others know what is going on, or what is the milestone, and when you're going to achieve it. Any difficulty, how you could help each other, how you get help from others. These are very important as well for this project. That's why I don't want to have an individual project, rather a group project. All right. So yeah, I mean, that's all for the lecture. If you do not have any other questions, you can just leave. Okay.
Thank you.
Yeah, no problem.